This session is about photons as a data set of internal, molecular, and intermolecular structure. And we're going to achieve this with lower energy to get those results. This is by Arno Viggen, and this is a patent-pending technology from my company, Scrunched Cubed Nanotech. Now, wavelengths provide both precision and energy. The shorter the wavelength, the better you can understand the size of things in today's microscopy. So to get e to the minus 12th energy, you need gamma rays. Now, of course, there's one problem, and that is these rays, A, take more energy, and B, that means danger, because that much energy will also destroy the sample. So what I'm proposing, and the part of my technology that's exciting, is that we can use visible light and ultraviolet light and excite to get those, and that those actually translate into the same information about 1 nanometer, or e to the minus 12 meters. And that's about the size of how electrons space. Now, all of this requires an understanding of the most important thing in subatomic physics, and that is the equilibrium. That is the Bohr hydrogen, which is 1 electron and 1 proton, settle at a distance of Bohr radius. It's called the symbol A sub O. Now, the real thing is that I analyze in my field acceleration physics stack all things based upon its position in the field. So that settling distance versus the particle edge is an important scaling factor. And at the right, you can see the ratios of that. And that is the ratio of the edge versus the equilibrium is what's called alpha squared. Alpha is called the fine structure constant. Although I don't like the wording constant, this is the equilibrium versus edge scaling factor because it applies in the exponents. It is not a constant. Hence, you will find this alpha in many places throughout chemistry, physics, subatomic physics, and even quantum physics. However, my presentations will never use that because I want to know actual distances and the ratios because I need to know where the particles are within the appropriate field. As such, I will always use this as the form A sub O over R sub E to the power n, including the power 1/2, which is the ratio you see to the right. But elsewhere, as you combine different ones, you'll see various exponents of n over 2. So 3 over 2, 5 over 2, 7 over 2. And that's for the comparison of different fields, but both using the same scaling factor. Now, by doing it this way, you also then can identify which ratio to use. Let me show you. So for example, the Rydberg is the basic formula for optical engineering. It is a formula that talks about squaring the number to get the difference in energy levels. However, I propose a slight variation on Rydberg to make it 3D engineering. And that is that it is the inside versus the outside distance. That is the position, the distance, plus the edge r sub e or minus the edge r sub e. If you think about that, those two will create different waves. Now, that r sub e is very, very tiny. That ratio is 1 over 18,778. Okay, so when you get to it, that inside versus outside distance at wherever that electron versus the nucleus sits goes at the two different cycles, and they continue to cycle until there's a node where they balance. That balance occurs at distance minus r sub e times distance plus r sub e. And that looks like a square minus the r sub e squared, or 18,778 squared. And so that factor is an adjustment at about 9 digits. So I can understand how Rydberg didn't notice it and didn't have equipment clearly that could get precision to that level. However, if you'd use this 3D harmonics of inside versus outside and replace the squares with inside versus outside, you will get all of the things that we need to understand photons as 3D engineering. So let's look at those things. When those particles have this d minus r sub e times d plus r sub e, you can still, that's a simple one harmonic. However, that's a single hydrogen with a single electron. And that system works fine, but we don't get any photons out of that because if something comes along, they just bounce around off of each other. Where we find extra energy levels is once we get to polypairs or Bose cylinder surfaces, which are the longitudinal rings that you find in electron distributions or electron subshells. As such, when you have different objects at different distances from the nucleus, they have to get a harmonic balance. So here's a simplified example. Obviously, this is not harmonic distances, but if you have electrons at 5 and 6 and 10 and 12, each of them will have various nodes, but there'll only be one node where all of those will stay in sync, and you'll get this tightest harmonic system. In quantum physics, we call this a spherical drum. And I call it a hemispherical drum because it is only sets based upon a nucleostatic axis of longitudinal rings per Bose's 1924 paper. But my interpretation of that as a common axis so that your harmonics end up with only one distance where it can vibrate and create the wave that we understand is inherent. You see, I think of duality as radial forces like electrostatic that are isotropic, the same in every direction, but also a force like weak force that is axial towards an axis and thereby anisotropic. And so the same particle can have both isotropic and anisotropic, just like a person can have height and weight inherent in them. But that anisotropic weak force can rotate and cause a wave function. And those wave functions for multi-particles will find harmonics out at certain permutations of the overall node. And those will stay in sync at unitary but different rates depending on the set. And those become spectrum. So let's talk about the simplest one of these, the polyhemisphere pair at 180 degrees. You see, two electrons have electrostatic repulsion. They want to be as far away from each other as possible. But they're still net attracted to the nucleus up to the Bohr radius, where the extra 1 over r math becomes a wall of repulsion to keep the electrons away in shells. So you end up with now a 3-particle system. And I'm using this because obviously that's the simplest system that I can do after hydrogen, and one that actually will have the harmonics to start these chains of spectrum. So based upon these, the white arrows are the inside and the outside dimensions, and that will generate the black arrows, which are somewhere way out there at the square of distance, where really d minus r sub e times d plus r sub e. There'll be these harmonic nodes, which I show as an open white circle. So that's the static system. However, important to spectrum is what happens in changes. What happens when you change that? You see, if you have a distance, but that wave starts going not 1x, but 2x in rotations, then what happens to the node? Well, the math from the nodes that I showed a couple slides before is that the node distance becomes the square of the 1/2. Or if you go 3x, then it'll be the square of the cubed. So that what happens is where we used to have one node going out there, we now have 4 or 9 or 16 nodes going out to the same position as the original node. So changes in energy levels, which I believe is these fixed sets of 1x or 2x of that base program. Remember 2 slides ago, let me again show. They must get in a harmonic set. However, that harmonic set then becomes a rotation rate or a wave function at a set basis. Now, those can actually fit into each other. As you can see, the 2x wave function does have that same node at 2007, but it's slightly different in nature. A rotation rate of 1.5 would not generate that same node at 2007, and thereby it would not have the quantized harmonic. So what happens though as you move those nodes closer? So here the Hast issue is what happens to the field. It's moving in from that 1 over n1 squared to 1 over n2 squared. However, fields are very balanced things. At that point, you must have a rotating force at the same energy, one rotation, so thereby one Planck strength, in this case H, okay, or H hat C, although the C will disappear as you'll see, going in the exact opposite direction. So the field has an imbalance that is not that is suspended until it hits something else. That lightning bolt rotating goes off at the speed of light, the C part, with the polarity because it's a rotation from the original electron, the counter force to that in a direction. And most importantly, to my technology, is that it's based upon a physical alignment of the electron, nucleus, electron, or a bonding to another nucleus and another electron if you're doing um, molecules, so that that photon tells me two different things. It tells me the exact alignment of the underlying particle that created it. Now, this doesn't help you in gas molecules that are bouncing around, but when we're trying to do physics of solids, which is the weakest part of DFT and other technical methods today, computational Monte Carlo, for example, knowing exact directions adds a frame of reference that we didn't have. Further, that distance that it moved has a math calculation based upon that internal distance. And that's the secret of the energy level that I started out with at the beginning. Because I can use this longer distance, I don't have to use gamma rays to get that. I can use the square of visible light or ultraviolet light, less divided by the permutations, to get e to the minus 7th, minus the permutations, to say e to the minus 6th, to give me an e to the minus 12 set of datum. So every photon that is generated is a data set. It is released outward, and so I know by its frequency, the internal distance of the system that generated it, the energy level, obviously by Rydberg, and further, by its direction, the orientation and line where that started. So that means they're all data. Every photon is a moment in history, okay? It tells us the alignment of the subatomic particles that created it. It tells you specifically, I can calculate their internal distance. It can tell you how many harmonic units are in that system because that's what generates the quantum rotation rate. And by the change in direction, it determines the initial distance. By the change of direction, it determines where they are, the particle alignment. Now, these computational methods are easy. They take lower energy. All I have to do is to understand existing photons, which we see coming off of particles. And we see photons not just from external layers, but also from internal layers. These are not the dangerous EM wave energies. They're from a known set of relationships for wavelengths and elements, and for molecules. And so we have comparable observations that have been built up over hundreds of years, so we can test these observations. But it also is a way to say, check a lattice material, because if you have photons coming off in a direction that is not the lattice orientation, that means there's internal errors. Okay, that means that there's something that's not built correctly in that lattice. You can check sequences by electrical charge, run an electron motion down there, and you can get the sequences by the photons coming off in order by time stamps. So rather than taking all the time to break down a DNA, an electron going through it might actually give us viruses or proteins in a simpler method. Now, we haven't finished these techniques, but that's the direction that we're heading and why we're excited about this technology. Now, there are computational challenges because you have multiple source particles. You can't always tell which data is coming from which origination, okay? Although direction and wavelength filtering tends to isolate it, and lower energies, so you're generating a limited set of photons, is the way that we overcome those challenges. We also have different layers. So what I have for the orientation datum may be adjusted as that photon moves from an inner layer to an outer layer. We also need to isolate the target. That means probably low temperature with blockage of vibration, external EM waves, or external magnetic fields, to make sure that I'm not changing those data, or I need to analyze that data by statistical methods to adjust for these factors where they occur. Thank you.